Hello, I'm Kim Dianyam, and I'm currently a first-year graduate student at Texas A&M University working towards a Master of Science in Computer Science. This is a video explaining some details about my undergraduate research project. Now, before we start, I need to mention that this video is an extension of my research paper, so if you haven't yet already, please read the paper. I'll likely link it in the description below. Once you're done with that, then you can come back here. Just to recap, the purpose of this project was to more or less create a proof of concept for a web animation framework or library called Anim Timeline that A. allows intuitive playback functionality and B. allows easy integration with normal front-end design and development. More specifically, we're creating the basis for a set of tools that make it significantly easier to create intuitive algorithm visualizations, especially for the purpose of education. The paper explains in great detail the underlying code that makes the Anim Timeline work, and in this video, we're going to give a visual demonstration of an algorithm visualization using Anim Timeline. We're also going to go over the structure of the code used to create the visualization. This video will go over the code as it was at the time of the paper, besides some small bug fixes, but after this, the code in the website might change a bit. I'll link the GitHub in the description, and I'll make sure the GitHub link points to the version of the code that you'll see here. Great, so with that out of the way, let's go ahead and get started. In this video, I'll cover various topics, so I'll include timestamps in the description or add YouTube chapters to this video as well. Let's start by giving a demo of the visualization itself. Now, presumably, a professor would have already taught the students about this algorithm and are giving more insights during the animation, but I won't be doing too much of that. I will, however, be pointing out some of the design decisions that were possible because of Anim Timeline's flexibility and ease of use. Before we start, realize again that the UI shown here might be different from what's currently on the site. That shouldn't matter much though, but what I'll be showing in this video does line up with what is shown in the paper so that there's no confusion with line numbers there. First, I want to point out that this transition between the multi-input form and the text input form actually uses an anim sequence, and the fade out from the job form to the fade in here uses 2 blocks. I just wanted to point that out because it turned out that the anim block and anim sequence are pretty handy on their own. In any case, I want to do this demo with a specific set of jobs, so let me use the text input form and copy down a preset that I have here. The first thing you'll notice is that the text will always be placed intuitively. Right here, for example, it makes sense for this text box to be placed right above these bars. We're not locking all the text to one corner of the screen. We're also using lines from the text box whenever we want to point to something specific, which helps clarify what we're focusing on. Another example of being really explicit and clear is the color coding. As we progress through, notice how we're color coding everything from the graphics to the text to even the text boxes themselves. Sorted job numbers are represented with red, C-array things are represented in green, and more. Also notice how, again, the text follows the action and the lines help direct the user. Another crucial task is highlighting. Whether it's through circling, pointing, highlighting, we need some way to reduce the mental overhead of memorizing what's important. Here, we use a highlighting animation to make sure the user knows exactly what's happening at a glance. No need to run their eyes over this left column and figure out where we are every time. We also continue using heavy visual cues to demonstrate parts of the algorithm. For example, this vertical bar technically isn't necessary, but it helps convey the idea of scanning through the list for a compatible job. Even the bold blue border on the right side of each job helps because it emphasizes each job's finishing time, and the slightly transparent blue makes it possible to see the grid lines underneath without being obnoxious. Additionally, this arrow changes its starting point depending on whether a compatible job was found. If a job was found, the arrow points from that row's header. If one wasn't found, it points from this bar. We could have just had it point from the bar no matter what, but the other way makes it more clear. I'll just run through the rest of these. Now, for the sake of not repeating myself, I won't keep talking much about design decisions here, but just notice how what we've discussed before applies here. In this part, we're explaining the brute force algorithm. We have nicely placed text, clarifying highlights, connecting lines, colors, etc. Here, we're explaining how we'll use a separate array for memoization. Again, neatly and intuitively placing everything and using animations to guide the eye. Moving on, this next part is where these good user experience habits become vital. Here, we're really making use of the localized text boxes, highlighting, and these lines. All of this is possible because all we need to do is specify which HTML elements we want to select and specify the animations we want to add to them, letting us create exhaustive yet visually appealing visualizations. And here's an example of a free line that continuously tracks its endpoints. Awesome! Now that we've done a demo of what the visualization we created looks like, let's look at the code to get a better understanding of how we structured it. The paper already went over how the tools themselves worked, so we're just going over how we utilized them. First, let's briefly go over the actual algorithm computation itself, which is done using job in JobScheduler. A job instance's main task is to store all the relevant data for a given job. That includes the start time, finish time, weight, job letter, sorted job number, compatible job number, and a reference to a job bar HTML element. It also has this method, findCompatibleJobNum, which finds the sorted job number of the current job's compatible job, if it exists. JobScheduler is where we perform the actual memoized weighted interval scheduling algorithm. Not the visualization, just the algorithm. I'll explain some of these parts in more detail, but for now, notice the C and M array as well as mechanisms for forming the list of jobs. The main method is perform_WEIS algorithm, which does exactly what we think. Sorts the jobs by finish time, fills the C array, initializes the M array with blank entries except for 0 in the first entry, and then runs our recursive method for computing the optimum weight. Here, we're actually performing the very same OPT subroutine described right here in the visualization. If MJ is empty, we need to fill it in, so we find the maximum between this job's weight plus the chain starting from the compatible job versus the chain starting from the previous job. Then we assign the result to MJ. Finally, we return whatever is currently in the MJ entry. You probably noticed that I'm ignoring these tree node things here. We'll talk about those later. For now, just know that the tree nodes are how we're saving each step of the algorithm. Anyway, let me repeat something I said earlier. All job and JobScheduler do is compute the algorithm. All of this happens before the visualization is even created. If we go to weisvisualization.js, we can see that clearly. Just to prove my point, I'll use this print method to show that the entire algorithm is run before we so much as create a single HTML element for the visualization. Look at the console. All the data is right here. We see everything, even the final answer. Now, why is this important? I'm making a point of this because it was a significant design decision. Originally, I actually created the visualization scene alongside each step of the algorithm, but that's a bad idea because A, I consider those two separate functionalities that are more clearly implemented individually, and B, isolating the algorithm computation like this let us utilize a great design pattern. We can store the entire course of an algorithm in a concise format, which is the tree we'll discuss later, and read from it to create our animated visualization. If we wanted, we could cache this tree data structure and use it later without having to rerun the whole algorithm, and the same could be said of other algorithms. We don't do that here, but that's just a thought for the future. Great! Now that we've taken a look at how Job and JobScheduler work, let's look at how we set up our HTML. How did we dynamically generate these elements that correspond to the user's input data? The answer is the HTML template element. A lot of the main pieces in this index.html file are enclosed in template tags, which allows us to create reusable chunks of HTML that we can clone and manipulate. We have a template for the job form rows, a template for job bars, a template for the rows in the time graph and other parts of the data display, and templates for job cards and job steps. At the beginning, once the user submits the form, we use these templates, the input data, and the algorithm tree to generate every single element that will ever be used in the visualization. Then the templates are discarded. So, for example, let's look at the template for a job bar, which is one of these blue bars. We'll be cloning this right here and changing the job letter data attribute to say, maybe, C, as well as filling in this template text to say, weight 2, for example. Another example is the template for the rows of the time graph. This is the template for one of these rows. At first, all that's in here is the code for the header, so notice the SJ number, the unsorted job letter, and sorted job letter. For some reason, I didn't create a template for the cells in here, but those are later generated and appended after the header regardless. The same process happens for this special row of times here, referring to the bottom row showing the times. This is the header, and the cells, which look like this, are appended later depending on the maximum time. Now, the next question we need to answer is, where exactly do we use these templates? When do we generate all of the elements for our visualization? Well, this is done in our SceneCreator. In our visualization file, notice that after we use the job scheduler, we instantiate the SceneCreator and call generate scene. Well, that's this file right here, and it does two things. One, it generates the elements in our data display, which is just everything over here on the left, and two, it generates the card tree, which we see here on the right side. At a glance, this looks like a lot of code, but it's actually pretty simple. It's long because we're spending all this code cloning the templates and filling in values. Some of the stuff here could probably be refactored too, but again, all we're doing here is filling in the data, nothing complicated at all. Let's look at some parts of Generate Data Display. The first thing that happens is actually inserting the cells, not duplicating anything yet. We're inserting these cells into the row of times and these cells into the template for these normal rows, just so our template is ready to be cloned. But notice one very crucial detail, the classes. It's vital that everything has some unique identifier or some data that when combined with another identifier forms something unique. This is how we're able to confidently select elements and, for example, tell each job bar to go to this cell or this cell or this cell, then later tell them to go to different cells, or tell this element that it needs to point to this element. The job of the SceneCreator is to not only generate the elements used in the visualization, but also to make selecting each element to animate very easy. If we examine the DOM and look at these rows, we'll see that they each have data that makes them intuitive to select. If I want this cell, I know I can select it by using a descendant combinator for time graph row 0 and time graph cell 1. If I want this cell, I can use a descendant combinator for time graph row 5 and time graph cell 10. If I want to know where this job bar should go at the beginning, I can look at the data attribute we set and use an attribute selector to look for the row where data job letter unsorted is equivalent. And if you're curious, that would look like this, where we select the row using an attribute selector and then specify the cell using the descendant combinator. We'll see these data attributes some more, but the beauty of this is that you, the developer, have free reign over what identifying information you need to make your life easier. In this project, we use data attributes and class names a lot for easily selecting elements for the purpose of animation. Alright, moving on, we start cloning some templates and filling in values. For example, we create a job bars in each graph row in this loop. When generating each job bar element based on one of these job instances, we simply clone the template for a job bar, which we saw here on line 251, replace any placeholder data, and add any data attributes that will make life easier. Then we return the new element and append it to our container for job bars. We do the same thing for the rows. We clone the template for a row, replace all the placeholder data, and add any data attributes or classes that will make selecting the rows easier. Just don't forget to remove templates when finished. We then do the exact same thing for these array visuals. Select what we need, clone templates, change the placeholder template text, add identifying information, and delete the template when we're done. Again, it looks like a lot, but it's really a lot of simple code. Now, there's a pretty clear optimization we can make for a situation where several pieces of text should say close to the same thing. For example, when filling in a lot of these text boxes, we know groups of these boxes will be using values corresponding to a particular job but are otherwise identical. Here, when finding the compatible job for job 4, we know all the references to the sorted job number will be 4, and we know that the text for the compatible job number will say 1. We may also want to fill in the end time or the start time multiple times for all we know. For that, there are these special fill classes. See how we have multiple spans with the class fill cur sjnum? After cloning this template, I can select all of those fillers by the class, fill it with the current job sorted job number, do the same with other things that can reasonably be filled like that, and add the new text box to the DOM. Rinse and repeat for each job. This tactic becomes especially handy when we're filling in text for the cards in this tree, where these different numbers are repeated very frequently. Speaking of job cards, let's talk a bit about Generate Job Tree and those mysterious tree nodes we created in JobScheduler.js. If you recall, during the course of the actual algorithm computation, we filled in these tree nodes with the relevant values and built up a tree starting from this root here on line 15. I'm actually not going to draw an example of what such a tree looks like because it's actually represented in the card tree here. The root card reflects the tree node where job equals the job instance for this current call. computation result 1 equals 11, and computation result 2 equals 9, m entry equals 11. In each of these recursive calls, we pass this tree node as parent node and append two child tree nodes to it, where non-terminal nodes correspond to job cards and leaf nodes correspond to job stubs. And then we continue that recursively until we have a tree of nodes that follows the course of the algorithm. When we put it like that, the process of creating the backbone for our visualization is pretty simple. The same strategy could be applied to other algorithms. You create a convenient data structure containing the intermediate values of the algorithm and store it for later. Then, in your SceneCreator, you can perform a traversal of your data structure where you generate the elements as you go. Here, we perform a pre-ordered traversal of our binary tree, where at each step, if we're handling a non-terminal tree node, we generate a new job card element, append it to its parent job card, and then make a recursive call for adding more cards or stubs. Or if we're handling a leaf tree node, we just create a job stub and append it to the parent job card. Well, how do we create job card elements and job stub elements? It's actually exactly the way we generate anything else. We clone our templates from index.html, replace any placeholder data, and add any data attributes or classes that will make life easier. And then we return the new elements and append them to their respective containers, in this case the child divs of the parent job cards. It's all the same things we did before. Now, looking at this, it should be clear how we can manage a system like this in an organized manner. It's long because we're filling in a lot of stuff, not because there's a ton of varying specialized logic. Yes, a lot of this could be refactored or modularized to create a public interface that developers can use to perform similar actions, and we will eventually do that in the next phase of our project. But that's not the main goal here. The next major topic I want to cover in this video is free lines. If we look at our HTML, there are free lines everywhere, and a lot of them are used multiple times. Just to give a reminder, this is a free line, and this is a free line, and they're everywhere, and we use them to point between any two elements on the page no matter where they are. Some of them even exhibit that continuous tracking feature that we explained in the paper, where an interval timer allows a free line to update its endpoints to account for movements not explicitly caused by animations, such as scrolling. Let's look at the CSS a bit. We already explained why these were the best style rules, but just to recap, these settings allow us the flexibility of placing the freeline SVGs wherever we want while preventing them from filling up the screen, interfering with right-clicking, or covering up the line itself. If we inspect the DOM, we'll notice that we can't directly right-click on one of these lines because of the pointer event's none. We did this because an SVG element actually looks like this. It not only covers up a different area than what the line covers, but it also occupies space that covers up other elements. It would be confusing if you tried to right-click here and pulled up the free line instead. Also recall that we're allowed to place the free lines comfortably around the DOM instead of being forced to contain them all in one central location because the update endpoints method in AnimBlockLine accounts for that initial offset from the top left corner of the page. The paper also explained that the special free lines with triangular markers, which we'll call free line arrows, need to link the line elements to the marker elements using IDs. The IDs naturally must be generated at runtime, which I will now show here. All we do is select each free line arrow and change the ID to something based on the current index, making it inherently unique. Easy. Now, finally, let's do a little code demonstration using AnimTimeline. After we set up our jobs and run the algorithm, create a scene, and do a bit more setup, we build our AnimTimeline using these two functions, AnimateDataDisplay and AnimateJobCard. They could be named better since they only set up the timeline rather than performing any actual animations, but I digress. Let's start with something simple, the beginning animation. This line interrupts from the bottom, pointing from the top of the first job bar to the bottom of the text box, and then the text box appears. Let me go ahead and open the console just so we can see the debug statements as well. This sequence is right here. Note that we're using array syntax to add these instead of using the constructors for AnimBlock and AnimBlockLine. Totally personal preference, I like it this way. But I allow the option for both. Anyway, here's where we set up the freeline animation. There's the code animation name, and here's where we choose the element for the starting endpoint and the element for the second endpoint as well as offsets. Now, quick aside, why is the null here? This is just something that made it a little quicker for me. If we look at animblockline.js, if one of those start elem or end elem arguments is null, it just chooses the previous sibling of the free line. That made it simpler to quickly tell a free line that one of its endpoints is its sibling text box, since I often grouped them in the same div. like here, for example. Nothing crazy, it was just to save some time. Anyway, now that we can clearly see that one endpoint is at the middle bottom of the text box, right? 50% from the left, 100% from the bottom, the same logic for how you would place an absolutely positioned element with respect to its non-statically positioned parent using CSS. Then for the job bar, it's 50% from the left and 0% from the top, see? Very simple line right here, especially considering everything that goes on under the hood. Then this text box fades in. Notice the block's prev option being set to false. That makes it so that stepping backwards will play both blocks in parallel, so they both exit at the same time. As we know by this point, the timeline isn't completely bidirectionally fixed. It lets us do fine-tuning to improve the user experience. Okay, that's great. This is simple and powerful, but something odd is going on here. How did the freeline know how to position this endpoint before the text box was rendered? We can't get any useful position data from an element's bounding box if it isn't rendered in the DOM. Well, this was actually already explained in the paper, but it bears showing here. If we look at base.css, we see that we have two separate rules for the hidden class. For almost everything on the page, hidden results in display none, in which case the element is not rendered in the DOM. But for the text boxes, hidden instead sets visibility to hidden. The element is still there on the page, but it is just invisible, meaning we can still use its positions. Okay, that's a lot to unpack for these two lines, but when you're building something, you won't be thinking about all of that. You'll just select your elements, write your anim blocks to an anim sequence, and then them to your anim timeline, and move on. Also, when we go through the process of making a more consolidated package for all of this code in our next phase of this project, things like the special CSS considerations and whatnot will be easier to handle. But here, we're just doing it all directly. Again, proof of concept. Let's do another example. Let's skip ahead to this sequence right here, when the jobs are being put back onto the time graph and sorted by finish time. This may look complicated, but I'll prove that it's not. First, we create a new anim sequence instance. Then, for each job, we're going to add to that sequence. What do we do for each job? Well, first, we need to figure out how to select the correct row, but we already know how to do that, right? Looking at the DOM, recall that each row has some identifying information thanks to the SceneCreator. In this case, we use the data job letter sorted. Easy, use the attribute selector. Each cell also has some identifying information because of their class names, the ones we set up in SceneCreator. Again, selecting it is easy now. Then, we're selecting each part of the row header here. After that, we add blocks to the sequence. Here, we get to see our translate animation in action. Moving the job bar to the cell is as simple as adding translate options and setting target LM. Meanwhile, underneath, all the magic is being taken care of, and we're able to rely on all of these default translation options since we're just using a simple translation with left alignment. At the same time as the bar moves, the old unsorted job letter does a wiping exit, see? Then, the sorted job number and the sorted job letter enter. Notice how we changed the duration on both of those to 0.25 seconds, which is half of the 0.5 second default duration, so that these finish by the time the job bar is in place. Just some nice polish. Anyway, since we're doing this for each job, those are all added to this single sequence. Then, this paragraph element within the text box fades out before the next one fades in. Finally, this anim sequence is added to our timeline. I'll do a few more examples to demonstrate some other features. Let's skip ahead to the part where we fill in the C array, which is a bit more complicated. First, I want to start at the point right before we fill in the C array. I want to point out that this part where this text fades out and this part where we begin the C array process are actually two separate sequences. If we look at the code, we see that this hiding part is totally separate. The reason it knows to autoplay into the next sequence is because of this continue next option we added in the anim sequences constructor. We also added some more continue next and continue prevs within the C array part to make transitions more seamless. Pay attention to the printouts down here. Stepping forward just one time from here, it plays this, and then automatically plays the next one. Stepping backward, rewind this, and then automatically rewind the previous one. Now let's go deeper starting here. Play, then automatically continuation. It's transitioning into the next C array explanation. Stepping backwards, rewind this, and then automatically rewind the previous. This autoplay functionality should be expected of any playback system, and it becomes incredibly handy both because it can make organizing code easier, and it can let you implement cooler scenarios than what I just showed here. Just use your imagination on that one. Now let's walk through how this set of sequences was done. For each job, we add 4 sequences. I'll pause during the auto continuation. 1. Bring in this green bar, highlight the job bar and JRA entry, and show some intro text. 2. Move this bar to visualize scanning the jobs and then change this text to reflect the result. 3. Point to the CRA and update the appropriate entry. 4. Fade everything out. Then 4 autoplays into the next sequence because of continue next. So let's start from the first sequence. Before anything, we select the text box, C-bar, which is this green bar, and this free line. The reason we do it outside of the loop is because we only need to select them once, animating paragraphs within the single text box, but it's just one text box, and we're reusing both of these. In the loop, after selecting the things we need, like the job bar, the JRA block we want to highlight, the CRA blank and value, etc., we set up this first sequence. First, we move the C-bar to the current job bar. We say preserve Y so that it only moves horizontally. That way, it's always level with the top of the graph. At this point, it's not visible, but like text boxes, we let the C-bar use visibility hidden instead of display none so that we can still manipulate it. Next, we highlight the job bar and JRA block and reveal the C-bar. If possible, you should always make it as clear as possible at any given moment in time what the user is looking at. If somebody walks away and comes back, they can tell exactly what's happening in this, which is also why using the fill text is crucial as well. It's best to make the sequences as specific to the current situation as possible. After that, we instantly change the paragraph in the text box to say the appropriate text and then fade in the text box. See? Then we add that sequence to the timeline. Second and third, we actually set up 2 sequences. This sequence is for moving the C-bar to a compatible job bar and highlighting it, or to the left of the graph if there is no compatible job. Then the text here changes to reflect the result. This other sequence is for pointing from the graph to the CRA, filling in the CRA entry, and changing this text to say, perfect, let's continue. If there was a compatible job, the freeline arrow will point from the sorted job number in the header of the row to add an extra level of clarity. If there was no compatible job, the free line will point from the bottom of this bar. Again, it's always nice to have some polish to make things more clear. Show the user you care, and it's easy to set up here. In the code, we have an if-else statement. If there's a compatible job, we add ANA blocks to the sequence for moving the C-bar to the right of that job bar, since we're focusing on its finish time, and highlighting the job bar, and we add an ANA block line to the other sequence for having the freeline arrow enter wipe and point from the sorted job number in the row header to the CRA entry, like this. Else, if there was no compatible job, the C-bar will instead move to the left of the time graph, and the freeline arrow will point from the bottom of the C-bar, like this. By the way, specifying alignment left here wasn't necessary since that's the default behavior. Anyway, then we add the blocks to those sequences for changing the text and revealing the number in the CRA entry, like this. Then, as usual, we add to the timeline. That might have seemed a bit more confusing because we were setting up 2 sequences at the same time, but just realize that it doesn't matter when you add blocks to sequences. What matters is adding those sequences to the timeline. This whole sequence is before anything in this next sequence. Fourth, we add a sequence to unhighlight everything and fade things out. We have another if-else statement to account for the compatible job existing or not existing, but after that, we fade out the text box and C-bar, unhighlight the job bar and JRA entry, and instantly hide the current paragraph since we're reusing this text box and simply hiding and unhiding paragraphs. That looks like this, except it continues into the next sequence because of the continue next option. Alright, that's enough examples from the data display. Now let's take a brief look at the cards and talk about how to set up this recursion. After setting up the sequences for the data display, the function animateJobCard starts the recursive process of adding the card animations to the timeline, but there are actually 2 relevant functions. The first is obviously animateJobCard, and the other is animateJobStub. Their tasks are essentially the same, except animateJobStub is specifically for animating the terminal leaf nodes, that's all. This probably could have been refactored to accomplish it in one distinct function, but again, not really relevant to the project itself. It was easier to just keep them separate. Let's look at animateJobCard. The first thing we'll notice is this long parameter list, but in the initial call, we only passed in one argument, the HTML element for the first job card. Well, this shouldn't be too surprising. For the root card, all we're doing is revealing this card with no connections. But for any child card or stub, like this one, we need a reference to this free line, a reference to this highlighted part, and a reference to this bullet so we know where to point this free line. This is parent arrow down, this is parent arrow source, and this is above bullet. These could have been named a bit better, but no matter. As we'll understand a bit later, the parent card is going to create part of the sequence and pass it to a child to finish, which is what parent anim sequence is for. As a generalization, it's how a typical recursive function may be set up. The first call has few arguments, and the recursive calls have more arguments to pass the extra context needed. We'll talk more about the recursion when we go to that part of the code. But for now, with that out of the way, let's walk through a bit of the actual function process. The first thing we do is create references to pretty much everything we plan to select. Maybe there's a more efficient way to do this, doesn't matter. Just make sure everything is named intuitively. That makes it easier to keep track of what's going on. The next thing we need to do is set up the sequence for introducing the card like this. The card fades in, we see this M, it gets highlighted, and this free line of text box appear. As we saw, child cards have a bit of help from the parent card in creating this first sequence. I won't go too into detail about how these sequences are set up because they're all actually really basic, as you can see from the code. But I just want you to see how powerful everything we've discussed so far is. This step-by-step explanation is possible just using the tools we looked at earlier. The free lines that can point between any two elements on the page, the localized text boxes, the highlighting, the exiting and entering animations to progress the visualization. Even selecting elements from the DOM is easy because of how everything is set up in the SceneCreator. We can add intuitive, identifying information like this 6 here to indicate job 6, so when we select it in the code, we just plug that in during runtime. Here, we can see continuous tracking at play, which can be turned on with track endpoints line options. Now let's take a step back for a moment and finish the discussion about recursion. This part is a little complex. Frankly, that's because I could have written it differently. I'll discuss the alternative, better approach later, but here's the gist of what we have here. Part of the sequence is created for the child, just this text box and line fading out, see? Then that partial sequence, along with the other references, the free line pointing down, this container, and this bullet, are passed into a call. Either a job or stub, no big difference functionally speaking. This sequence that gets passed down gets finished up and added to the timeline when the child card first starts. However, what I didn't mention before is that the child cards or stubs return some things to pass back up to their parents. Once a child is finished, we see this animation sequence where this free line disappears, this value gets unhighlighted, and the text box and its free line disappear. Then it immediately continues into animating with the parent card. Here's how it was done. If we scroll all the way down to the end of Animate Job Card, if the current card is a child, as opposed to the root, then we start setting up a sequence that begins with that first part. Then we return the sequence, along with a reference to the free line arrow pointing up the tree and a reference to this container, so the parent card can finish up that sequence as we see here. We're storing those return things and adding this remaining part to the sequence. Now, for the second recursion, which looks like this, it's slightly different because this red dotted free line points from the sibling card's bullet instead of the parent card's bullet, but other than that, it's the exact same idea. Earlier, I said this could have been written a lot better. That's because this process of passing anim sequences and elements up and down the tree is needlessly confusing. Even though this is perfectly valid, we could have just made them separate sequences and used the continue next and continue pref autoplay functionalities to make sure they play into each other. Why didn't I do that? The reason is simple. I actually don't think I had that autoplay functionality implemented when I wrote this part of the code. I didn't want to refactor this though because I want the line numbers to match up with whatever is in the research paper. Just for this video at least. Next, I want to demonstrate skipping to specific steps. This is not referring to enabling skipping like this and just going back and forth. I'm referring to this skip to method in anim timeline. It's actually not used anywhere in this visualization, at least not right now. The feature is finished, but I only used it for debugging purposes in this project, so I'll just use those little tests to show it off. Recall from the paper that we can set tags on anim sequences like this. We can then skip to the closest sequence with a particular tag using anim timeline.skip2 and passing in the tag, plus an optional numerical offset. I have a bit of extra code set up to handle the playback buttons, but don't worry about that. Just know that this skip2 function is calling the anim timeline skip2 method directly. So let's try skip2 start. And there, we see that it really did skip to the sequence with the tag start because the very next sequence we play is that one. Now let's try skip2 found max, which I set on sequences that just solve for the maximum value of their chain of jobs. Let's generate and run. There we go. It's the following sequence where the first M entry is filled. Okay, we've covered a lot so far, but we're almost done with the code demoing of anim timeline. The last thing I want to talk about directly regarding anim timeline is implementing highlighting, which wasn't really explained in the paper. If we look in animblock.js and look at the preset animations for highlighting and unhighlighting, we see that all they're doing is changing the background position from 100% to 0% or 0% to 100%. What's going on there? Well, if we look at the CSS, we see this class highlightable that applies some styles to the element's background. To sum this up, we're using this gradient to split the background color into half yellow and half transparent, and it's a hard split. There's no gradual color fade because the yellow ends right at 50% and the transparent starts right at 50%. What we can then do is double the background size, plus a bit of leeway to prevent pixel error. So now the element's background width is split into two regions of yellow and transparent that are the same width as the element. So when background position is 100%, the transparent part is fully there, and when background position is 0%, the yellow part is fully there. If we transition between 0% and 100%, the background color slides, creating the visual equivalent of highlighting. Anything we plan to highlight in the visualization has this highlightable class applied to it. That's it for the code demonstration, demonstrating how we made use of anim timeline to create a visualization. Before we finish things up though, I want to touch on how we set up the playback buttons. The buttons were set up entirely separately. They aren't actually part of the anim timeline here. Rather, they kind of hook up to the anim timeline and call the playback methods like toggle pause, step, etc. Now, realistically, there would be some preset functionality to hook up these buttons for the developer, and you would be able to just use them, and that will likely be done in the future version of anim timeline. Here, though, everything was hooked up manually, but this serves as a good demo for how to go about setting something like this up. The first thing I'll talk about is these class names that can be applied to the buttons. Notice that there are a lot of them that seemingly do the same thing. There are two different classes for being pressed, and we have several classes for disabling. The reason for that is that there are multiple different conditions that can trigger certain states, and these conditions may or may not be simultaneous. For example, I could be at the very end of the timeline, in which case the forward button should be disabled. While there, I could also press pause. If I then unpaused, the incorrect behavior would be to enable the forward button, because I'm still at the end of the timeline, right? This should stay grayed out. Having all these classes is the easiest and most readable way to ensure that different conditions don't erroneously interfere with each other. These can stack on top of each other so the stylings are always correct. Also, assigning the class names to these constant variables adds some flexibility and prevents typos. Now, when handling the functionality of the buttons, it's actually some pretty basic logic. For the forward button, if the timeline is currently stepping, or it's paused, or we're at the very end, we can't step forward. Otherwise, we call the anim timeline step method and go forward. Easy. Everything else here is for adding and removing classes. I add pressed to the forward button, which pretty much turns it red. Remove disabled from edge from the backward button. No need for an if statement to check if the class was actually there because JavaScript will run it just fine either way. Add this disabled from stepping to the backward button to essentially gray it out, and disable the pointer on the forward button because we don't want to gray it out, we just want to disable the pointer. Then, conveniently enough, our step method returns a promise, so we can chain on a then where we handle the classes again. Overall, the same thought process applies to hooking up the other buttons. These separate classes make it easier to map out the different conditions and how they affect the playback states. I didn't even need to draw a state diagram while coding this, but if I did, it would naturally reflect the different classes here. Great, that's all there is to ensuring the UI and the code are intuitive. But there's another thing we need to consider for a good user experience: keyboard shortcuts. Ideally, there should be keys that map to the different buttons so that a professor or student doesn't have to move their mouse to the buttons every time. Case in point, I've been using the keyboard shortcuts almost the entire time. The easiest way to do this is to add a key down event listener to the window object and map the keys there using control flow statements, and within each block, simply dispatch a mouse down event to the appropriate button. As a side note, the dispatch event method is available on any HTML element and allows you to dispatch events programmatically. Speaking of dispatching events, one thing to be careful of is making sure mouse down only triggers on left click. By default, mouse down detects any button on the mouse, even the middle mouse button. Luckily, the event for mouse down comes with a which property, which is equal to 1 if the left mouse button was pressed, or undefined if none of them were, which would be the case if we manually dispatched the mouse down event. So this is a left clicker key and shows that only keyboard shortcuts and the left mouse button can trigger button presses. Nothing else. Now, finally, let's talk about why there are two different classes for being pressed. Well, here's why. It's because the fast forward button turns green instead of red. From a design standpoint, that alone tells you that there's something different about it. The difference is that it, unlike the other buttons, needs to be held down. To handle the functionality of holding down the button, there is a bit of fancy logic to make sure different combinations of holding and releasing the mouse or the keyboard shortcut F work as expected. But essentially, there are two separate variables for whether the fast-forward F key is held down or the button is held down. At any given point, if one or both are pressed, the playback rate is increased. That's handled with the mouse down and key down events. If either one is released, if the other is still held down, fast forwarding is still enabled, but if both are released, the playback rate is reset back to 1. That part is handled with mouse up and key up events. And with that, we finished a fairly in-depth look at how to set up an environment for creating an algorithm visualization and use a system like Anim Timeline to interact with it. We also saw how detailed and exhaustive the weighted interval scheduling visualization we created is, and how robust the playback functionality is. Now, do keep in mind that the original goal was more to demonstrate a proof of concept, which is why things like the fill classes, playback buttons, CSS class considerations, and things like that weren't automatically set up through Anim Timeline itself. The improved version of this framework will consolidate a lot of the boilerplate code, as well as build upon existing functionalities and add new ones. But this early stage of Anim Timeline, as it is in this video and the research paper, shows how beneficial a system like this is. This was quite a lot of fun to make and figure out, and hopefully you enjoyed following along. Thank you.